Okay, welcome back. And now we're going to start Unit 7A, so Chapter 7, Section A, and we're going to start the fundamentals of probability. Okay, so now that we've spent some time talking about statistics, now we're going to turn our attention to probability, which is a big part of statistics. Much of what we do with statistics relies on probability. Okay, so let's get started. Okay, so here's some definitions. Of course, we always have to start with definitions. Outcomes. Outcomes are the most basic possible result of observations or experiments, and these are, random experiments. So, for example, if we toss two coins, one possible outcome is that we get heads on the first coin, tails on the second coin. Another possible outcome is we get tails on the first coin and heads on the second coin. And then there are two other possibilities, right? We could get both heads or we could get both tails. Now, an event is defined by a set of outcomes, right? It could be one outcome or it could be more than one outcome that can cause an event to occur. So an event is defined as some outcome, some defined outcome that consists of one or more basic outcomes, if you want to look at it that way. For example, if you toss two coins and we want to define an event as counting the number of heads, then that changes how we would write some of the outcomes, right? Because now we're counting heads. So what are the possible outcomes? What are the possible outcomes for the event, right? So you could get, if you're defining the experiment this way, your outcomes would be either you get 0 heads, 1 head, or 2 heads, right? And so if we look at the event, we define the event of getting 1 head, right, on a flip of 2 coins, then there are 2 outcomes that will make that event happen, right? So we could either get a heads on the first flip and a tails on the second flip. That results in 1 head. Or we can get a tails on the first flip, a head on the second flip, and that will give us the event that we're looking for. So there are 2 outcomes that if either one of those outcomes occur, the event of getting 1 head, exactly 1 head on the flip of 2 coins happens, right? So that's important to understand when we discuss defining an event, right? Now, we could define an event as getting no heads, which would also be the same as the event of getting all tails, right? And so there's only one way, one outcome that will do that, okay? That we get, in fact, the only outcome that will give us the event that we have 0 heads is the fact that if we get both tails. Okay, so those are the definitions of outcomes and events. So let's consider the family of 2 children. We want to list all the possible outcomes for birth order of boys and girls. If we are only interested in the number of boys in the family, what are the possible events? Okay, so what are the possible outcomes for birth order? Well, let's write them out. So we could get a boy on the first birth, and we could get a boy on the second birth. Or we could get a boy in the first birth and a girl in the second birth, okay? And then, of course, we could get a girl first, followed by a boy, or we could get a girl first, followed by another girl. And so then these are the total possible outcomes. There's no other outcome for birth order than these 4, okay, in this situation when we're dealing with only 2 births, okay? Now, what are the possible events? Well, there's all kinds of possible events. We could count the number of boys, we could count the number of girls, we could say, um, um, we can define different events. Okay, so let's see what they have here. So, okay, so there's the possible outcomes, just like I said. Okay, now, so because we're asked to consider the total number of boys, then the events that could occur is that we could either have zero boys, one boy, or two boys. So now here's the thing. The event that we get zero boys, there's only one outcome that will give us no boys, and that's girl, girl. There are two outcomes that will give us one boy, and that's going to be either we get a boy on the first birth followed by a girl, or we get a girl followed by a boy. And then the event that we get both boys, well, there's only one outcome that will give us that. Okay. Now, how do we express probabilities? A probability is an event, or the probability of an event, which we denote using the symbol, right? P of, right? So normally we write an event using a capital letter, typically A or B or whatever. So it's a capital letter, and so P of A is the probability of the event A. And probabilities are always between 1 and 0, inclusive, which means it could be 0 or it could be 1, and anything in between. Okay, and so this is the way we write it. So a probability of 0 means that it is impossible to happen. A probability of 1 is that it is certain to happen. It has to happen. Okay. Anything that's between 0.5 and 1 we say is likely to happen. And anything between 0.5 and 0 we would say is unlikely to happen. If it has a 0.5, that's a 50-50 chance, right? So probability of a half. Okay, and again, this is a general rule for probability. Okay, much of this will change depending on expert opinion in the industry that we're dealing with. Okay, now so here's the theoretical method for equally likely outcomes. So this is based on, and this is one of the definitions of probability. It's the theoretical definition, and it's based on the assumption that outcomes are equally likely, that they have every outcome has the same chance or the same probability of occurring. Okay, so in this case, the way we calculate a probability is first we count the total number of possible outcomes, right? We've got to get two numbers. One of the numbers we need is the total possible outcomes. And then two, what we do is among the possible outcomes, we count the number of ways that the event that we're interested in can occur. So how many outcomes in the sample space, so the sample space is all possible outcomes, and then out of all possible outcomes in the sample space, how many of those outcomes will result in the event A that we're interested in? So that's the other number, right? So now we've got our two numbers. We've got the total possible outcomes, and we've got the total number of outcomes that will occur, that will result in A occurring. Okay, and then what we do is we determine the probability by taking the ratio of those two numbers. We take the number of outcomes that give us the event that we're interested in, A, divide that by the total possible number of outcomes. And that will give us the proportion of the total possible outcomes that will result in A. And that's what we get with probability. That's the theoretical definition of probability. So now let's look at an example and let's apply this definition of probability. So it says here we want to find the probability of exactly one head when you toss 2 coins. Okay, so first we got to write out the sample space, right? So we want exactly one head on on 2 heads, right? So what do? We write out the sample space, right? Write out the total possible outcomes. Okay, so what can we get? We get heads, 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 tails, tails, heads, tails, tails. Okay, so there's our 4 possible outcomes. Now, how many of those outcomes gives us the result of exactly one head? And that'll be this one and this one. This is exactly analogous to the birth order example, if you notice. So now, what do? We take the probability and what do? It's the probability of exactly one head. And how many outcomes give us exactly one head? That's going to be 2. And how many possible outcomes are there? There are 4. And so the probability is 1/2. Now, what about getting a 3 on the roll of a 6-sided die? Well, the same thing. We used the sample space, right? So how many possible outcomes are there on the roll of a 6-sided die? So the total number of, or the total possible outcomes is going to be what? You can either get a 1, a 2, a 3, a 4, a 5, or a 6. And how many of those outcomes will result in a 3? Well, only 1. So if we use the theoretical definition of probability, the probability of getting a 3 is equal to what? How many ways can you get a 3 on a single roll of a die? Well, just one way. How many possible outcomes are there? 6. And so the probability is 1/6. All right, let's look at playing cards. There are 52 playing cards in the standard deck. There are 4 suits known as hearts, spades, diamonds, and clubs. Each suit has cards that have the numbers 2 through 10, plus the jack, queen, king, and ace. So for a total of 13 cards for each suit. So if we take 13 for each suit, 13 times 4 gives us 52. Notice that hearts and diamonds are red, and spades and clubs are black. So we have black cards and we have red cards. So there are 26 red cards and 26 black cards. So now, if you draw 1 card at random from a standard deck, what is the probability that it is a spade? So let's use the theoretical definition of probability, assuming that each card has the equally likely chance, right, is equally likely to be picked. Okay, so we can apply the, which is, again, that assumption is reasonable, okay, because we're choosing at random. Okay, let's use the theoretical definition. And so the first thing we just, okay, so let's do this. So probability of what? That it's a spade, right? So we'll use S. Now the question is first of all, what number goes on top? The number that goes on top is the total number of ways that will give us a spade. Well, how many cards could we choose from the deck of 52 cards that will result in a spade? How many spades are in the deck, in other words? So there are 13, right? There are 13 spades. in the deck. And how many total cards are there in the deck? Well, it's a standard deck of 52 cards. And so now, in this case here, this fraction's pretty, not big, but it's, we can simplify this, right? Because 13, like I said before, 13 goes into 52 4 times, right? Because 4 times 13 is 52, so this reduces to 1/4. So the probability of choosing a spade randomly from a deck of playing cards is 1/4. Okay? Now let's look at a more complicated example. This one deals with 4 children, and we want to look at birth order. Okay? So in this case here, we've got to write out the sample space. Now the key is being able to write out the sample space for something like this. So there's a pattern, and so if you learn the pattern works for all of situations like this one, okay? Where there's only 2 possible outcomes, okay? And so if you realize the pattern, then you'll realize how many you have. Plus, realizing that in this case here, for things like birth order, flipping coins, again, where there's only 2 possible outcomes, the same pattern occurs. Excuse me. Okay. And so we could start with all girls, right? And then we can just cycle through with the boys. So if we do girl, 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 and then girl, 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 boy, girl, girl, boy, girl, 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 boy, boy. Now notice that the last 2 went through the same pattern that we did before when we only had 2 children. Okay, so now what happens is those last 2 positions right here are the only possible outcomes for those last 2. So now what we're going to do is we're going to change the 3rd position to a boy and do the same thing. So now we're going to do girl, boy, girl, 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 boy, girl, boy, girl, boy, boy, girl, girl, boy, boy. Oops, hold on. Girl, girl, girl. Oh yeah, boy, boy. So that's right. Okay, so notice again we went through the same pattern. Okay. And now what we're going to do is we are going to change the first one to a boy, and then change this one to a girl, and then go through the same thing. So if I want to do this, I could do this, because those are going to stay the same. And then I'm just going to cycle through girl, girl, girl. Oops. Girl, boy, boy, girl, boy, boy. And then finally the last 4, now I'm going to change them to both boys, the first 2. So notice I'm going through the pattern for the first 2. So now I'm going to go girl, girl. So let's do boy, 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 girl, boy, boy, girl, boy, boy. And so there are the 16 possible outcomes that we see in the table here. And again, what we're interested in is the probability of having 2 girls and 2 boys, which is exactly the same as just saying, hey, what's the probability of having exactly 2 girls or the probability of having exactly 2 boys, okay? So if we look at it, we split the scenarios up in all possible categories, right? So all girls, 3 girls and 1 boy, 2 girls and 2 boys, 1 girl and 3 boys, or all boys. And so now we've categorized how many of each of the 16 possible outcomes go into each event. And so now we can easily count, 1, the total possible outcomes is 16. So we know the probability of getting exactly 2 girls and 2 boys, or just 2 girls, right, is going to equal what? How many ways can we get exactly 2 girls and 2 boys? There are 6. So it'd be 6 out of the total 16 possible birth orders. And so we can reduce this to 3/8 okay, and at this point we can also write the probability as a decimal. And when we start getting into 3/8, like 1/8, like 1/4, 2/3, you know, 1/3, 1/6, those are simple enough fractions that we usually will leave them as fraction. But as we get to more complicated looking fractions, we always write them as a decimal. Okay, so just be aware of that. All right, so let's go on. All right, now the other definition, there are 2 definitions of probability. The second definition is based on relative frequency. It's called the empirical definition, or the relative frequency definition or method. Okay, and this is based on data. Okay, and so in this definition, what we use is we use the number of outcomes in a trial, like an experiment. Okay, so we collect data on something, and then we count the number of outcomes in the data set that result in the amount, that result in the event that we're interested in, and we divide that by the total number of outcomes in the experiment that we did, how many trials we did. Okay, so the empirical or the relative frequency definition is just the definition of relative frequency, right? So we talked about relative frequency. We know how to calculate a relative frequency. So now what we're going to do is we're going to use that relative frequency in this case, because what we're talking about is random processes, right? Random results. And so if we're dealing with experiments that involve a random process, then we can use the relative frequency definition as probability. And that's what we're going to do. So let's look at the test of a fair coin. If you are interested in only the number of heads when tossing 2 coins, then the possible events are either you're going to get 0 heads, 1 head, or 2 heads. Suppose you repeat a 2-coin toss 100 times, and your results are as follows. You get 22 times, you get 0 heads. 1 head occurs 51 times, and 2 heads occurs 27 times. And then what you want to do is, these are the relative frequencies, right? Or these are the frequencies in this experiment. What you want to do is you want to calculate the relative frequencies and compare them to what you would theoretically should get. And then based on that comparison, decide whether these coins are fair. Okay? So let's set up our relative frequencies. So if 0 heads, we know the theoretical probability is 1 out of 4, or 0.25. The theoretical probability of 1 head is 2 out of 4, or a half. And getting 2 heads is 1/4, or 0.25. By the way, notice that all of these probabilities add up to 1. Okay? And they should, but we'll talk about that. All right. Let's compare this to the relative frequencies now. So we got 22 heads out of 100 flips. Or excuse me, we got 22 times that we got 0 heads out of 100 flips. So that gives us a probability of 0.22. 51 flips resulted in 1 head. So that gives us a relative frequency of 0.51. And the relative frequency of getting exactly 2 heads was 27 times out of 100. So that gives us a relative frequency of 0.27. So now we're going to compare these. So we're going to compare the 0.22 to the 0.25, compare the 0.51 to the 0.5, and the 0.27 to the 0.25. And we look at these and we say, okay, these are pretty close to what we would expect them to be based on theoretical probability. And so since they're fairly close, there is no reason to suspect that the coins are unfair. Now, there are 3 approaches to finding probability. One is the theoretical probability. And this, again, is based on the assumption that all outcomes are equally likely. Okay? We have to decide whether that is reasonable or not. Okay? In most of the cases we've been dealing with, it is very reasonable to believe that all the outcomes are equally likely. Okay? Because we're using a simple random sampling, right? In most cases. Then there's the relative frequency probability. That's based on observations or experiments. It is the relative frequency of an event, right? That's all we're doing is calculating the relative frequency of an event that we're interested in. And then the other one is subjective probability. This is an estimate based on experience or intuition. Okay? So if I say, for example, 95% of financial planners excuse me, if I say let's say if I say, okay, 95% of financial planners promote the idea of accumulating a nest egg for wealth, then that would be a subjective probability based on my experience and intuition, reading and whatever, okay? Or if you go to your doctor and you're diagnosed with a disease and the doctor says that there's an 80% chance that you'll make a full recovery, then that is also a subjective probability based on that doctor's experience and intuition in his field, right? Unless he pulls out data, experiments or whatever that tell you. So in most cases like that, we would call that subjective probability. Or if we look up the rain and say, yeah, you know what, I think there's probably a 70% chance of rain, right? You look out the window, there's gray clouds, and like, yeah, it looks like probably, I'd say a 70% chance of rain. That's subjective probability. All right, so now let's look at this example. It says, identify the method that resulted in the following probability. It says, I'm 100% certain that you'll be happy with this car. Okay. I'm 100% certain you'll be happy with this car. Well, what kind of probability is that? That's going to be subjective, right? Because this is probably the salesman, and he's saying, you know what? I know you're going to love this car. You're just going to love this car. Based on government data, the chance of dying in an automobile accident during a 1-year period is about 1 in 8,000. What kind of probability is that? It says, well, it's based on government data. So that's telling us that this is going to be based on what? Empirical data. Empirical, which means this is going to be what? Relative frequency, or in other words, the empirical method. And then C, the probability of rolling a 7 with a 12-sided die is what? Well, how many 7s are there? There's only one 7. How many possible outcomes are there? 12. So this is using theoretical probability. Because why? Well, one is we're rolling a die, right? We're assuming it's a fair die, so each side is equally likely to come up. And so this is using theoretical probability. Okay, now let's talk about something called the complement. So we've been talking about the probability of an event occurring, but now let's talk about the probability of an event not to occur, right? So in other words, instead of talking about the probability of A, what about the probability of not A? What about the probability that A doesn't occur? Well, then we're going to use what we call the complement rule, which is based on the fact that all the probabilities must add up to 1, right? So if we add up all the probabilities in a sample space, all the possible outcomes in a probability experiment, then all of the probabilities should add up to 1. That needs to happen for a valid probability experiment. So if we're talking about an event occurring versus an event not occurring, well, those two probabilities should add up to 1 because there's no other outcome, right? So for example, if I randomly select a deer and I'm interested in whether it's healthy or unhealthy, well, there's no other possible outcome. Either the deer is going to be healthy or unhealthy. If I'm talking about birth of a baby, well, then and I'm looking at the gender, right, of the baby, then there's only going to be either male or female, right? So there's no other possible outcome, right? So either the baby's going to be a boy or not a boy, okay? If I'm talking about flipping coins, right? Either I'm going to get heads or tails, right? So that means I'm either going to get a head or I'm not going to get a head. I'm going to get a tail or I'm not going to get a tail. So there's only two possible outcomes. So using the probability of those events, we know that those events should add up to 1. So we know the probability of A plus the probability of not A, and I'll just write it out for now. That must equal 1. And so if I want the probability of not A, then I just subtract probability of A from both sides. So the probability of not A equals 1 minus the probability of A, which is what we got up here. And that's what we call the complement rule. Okay? And so if I know the probability of A and I want to know what the probability of not A, all I have to do is subtract the probability of A from 1. And that's the complement rule. Okay, so since the probability of a family of 3 children having 1 girl and 2 boys is 0.375, what is the probability of a family of 3 children not having 1 girl and 2 boys? Well, again, either this event is going to occur or it doesn't occur, right? So if the probability of, and let's call this, we'll call this A, right? Having 1 girl and 2 boys, we'll call that event A, right? And so we want the probability of not A, and I'm using the symbol, the apostrophe, we call that prime, so A prime. This is not A, okay? There's other ways of writing it. Some textbook use with a C at the top for complement, so A complement. So again, just something for you to know. And so the probability of not A is going to be 1 minus the probability of A. And since we know the probability of A is 0.375, then we're going to do 1 minus 0.375, which is going to give us 0.625. And so the probability of not getting 1 girl and 2 boys is 0.625. All right. Now let's talk about a probability distribution. So a probability distribution is nothing more than a table that consists of 2 columns. The first column we call X, and X represents all of the possible outcomes of the probability experiment, depending on how X is defined. And then the second column is the probability of X. And that's the corresponding probabilities for all of the outcomes in the column. So the first thing we do is step one is list all the possible outcomes, and then use a table or figure to help you. And then two, identify the outcomes that represent the same event, and then determine the probability of each event. And then make a table listing each event and its probability. The sum of all of the probabilities, again, must be 1. Okay? Okay, so it says make a probability distribution for the sum of the dice when 2 fair dice are rolled together. What is the probability? What is the most probable sum? Okay, the first thing we need to do is we need to write out all the possible outcomes for rolling 2 dice. Okay, now there are 36 possible outcomes for rolling 2 dice. And the way we get that is by taking the fact that there are 6 outcomes possible for 1 dice, 6 possible outcomes for the other dice, and we multiply those two results. And so if we draw a table, we can see that we can, if this is like, let's say the first dice, the first die versus the second die. So if you get a 1-1, right, that's going to add up to 2. If you get a 2 and a 1, that's going to add up to 3, right? And if you get a 2 and a 1, that's going to add up to 3. So you can create this table of 36 possible outcomes, and you can just add up the face values of the dice and get your sum, right? So notice that the sum, the smallest sum you can get is 2, the largest sum you can get is 12, and you can get all of the integers in between. So notice on the diagonal here, you get 3, and then on this diagonal here, you get 4, and then on this diagonal here, you get 5, and then 6, and then 7, and so on and so forth, right? And so what you can do is count the number of outcomes that give you each sum. So for each, let's say for 2, there's only 1 outcome that gives you 2. For 3, for the sum of 3, there are 2 outcomes. For 4, for the sum of 4, there are 3 outcomes. And it goes up by 1 each time. Right? And then until you get to 7, and then it goes back down, because with 8 you have 5 again, so it starts going back down. And it goes back down by 1 until you get to 12, which is only 1. Okay, and so you use this information to create your probability distribution. Okay, because you take all of the frequencies, or all of the outcomes rather, that give you each event, right? And you just divide each one by 36, and that gives you the theoretical probability for each one. And so notice how they all add up to 1. And so the most likely outcome is going to be 7, because that has the highest number of outcomes. Okay, so that one gives us a probability of 1/6. All right, so that's how we do a probability distribution. So the last topic we're going to talk about is odds. Odds are the ratio of probabilities. Okay, so to figure out the odds, all you're going to do is you're going to divide two probabilities. Okay, the two probabilities are the probability that the event will occur versus the probability that the event won't occur. That's how we get our odds. Okay, so for odds for an event, so key thing is going to be the probability of A divided the probability of not A. The probability of odds against an event occurring is the reciprocal of that. Okay, so we just flip the division. Now, in gambling, we always use the terms odds on, so is the same as for odds against. Okay, so if you're ever at a casino, if you gamble, I'm not a gambler, but if you're a gambler, if you hear the term odds on, that's the same as odds against. Okay, so what are the odds for getting two heads in tossing two coins? What are the odds against it? So, okay, so if we look at the odds for, okay, again, that's probability of A divided by probability of not A. So let's do that first. So we know the probability of getting two heads is 1/4, right? We should know how to get that now. And the probability of not getting two heads is the complement. So we know that that has to be 3/4. And so notice that the 4's drop out because we're dividing two fractions and the denominators are the same. We get 1/3. Now, the way we would read this is 1 to 4. Okay, so the odds for getting two heads is 1 to 4. Okay, the odds against then is just going to be the reciprocal of that. So if we do the odds against, it's just going to be 3/1, which is going to be 3-1. So that's the one that we hear. Oh, the odds are 3-1. There's a 3-1 odds that Lucky Charms is going to win the race, right? Or there's a 3-1 odds that the Bears are going to go to the Super Bowl. Not really, but you get my point. Oops, I made a mistake here. I wrote 4 here. I was thinking 4. This is 1 to 3. All right, now let's look at a horse race. It says, at a horse race, the odds on Blue Moon are given as 7 to 2, okay? And you bet $10 and Blue Moon wins. How much will you gain? Okay, so the way to figure this out, we have to understand what the odds mean. So the odds on, which is the same as odds against, right? So the odds on Blue Moon are given as 7 to 2. So that means for every $2 you bet, right, you will get $7 back if you win. So we have to figure out, how does that apply to $10? Well, in this case, we're just going to say, okay, well, how many $2 bets, in essence, are we making? In this case, we're making 5. So that means this would be what? $10, if we win, would be $35, right? All right. And that's what this says, right? For every $2 you bet, you're going to gain $7 if you win. You make a $10 bet, that's like making 5 $2 bets, which means that if you win, you're going to get 5 times $7, which is $35, and you also get your $10 back. So you're going to receive your winnings, the gains, plus your original money that you paid for the ticket. Okay. Now again, I don't know if that works that way in all gambling or not, but in this example, you get your money back. All right, and that is it. So that wraps up this section, and you enjoy the rest of your day, or I'll just watch the next video. We'll keep things going. I'll be here.